Welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I'm Professor Rakesh Singh Shetterman. So in this lecture, we'll discuss about the boundary conditions for electromagnetic fields. First, we'll consider the boundary conditions for electric fields. So these are the two figures we'll be using for solving the boundary condition for electric fields. So what we'll see is that most of the boundary conditions are derived from the Maxwell equations, and the boundary conditions will be deciding or finding would be for the electrodynamic fields. It will not be only for electrostatics or magnetostatics. It will be for electrodynamic fields. Let us try to understand these two diagrams here for the boundary condition for electric fields. First string, this is the x-axis, and this is a y-axis, and this is our z-axis. So now the interface is at z is equal to 0. When z is equal to 0, we have interface. Region 1 is when z is greater than 0. Region 2 is when z is less than 0. So we have a region 1 when z is greater than 0. We have a region 2 when z is less than 0. We have an interface at z is equal to 0, and we'll try to consider a closed contour P, Q, R, S, P, which is in the xy plane at z is equal to 0. So in order to derive the boundary conditions, we need to apply Maxwell equation. Here we'll consider Faraday's law over the loop PQRSP. So this is the Faraday's law. You have line integration here, E dot dl. Right hand side you have a surface integration of del by del T of magnetic flux density. So let's do the line integration in the left hand side first. So now we are doing line integration over this PQRSP. So the contribution from the PQ line would be, so it's E dot dl. So electric field in region 1 is E1. When you do E dot dl, you get E1T into length of this. Length of this is assumed as L. So now you also do line integration for this, but fortunately ice is tending to 0 at the interface. So when I assume that ice is tending to 0, the contribution from the QR portion is negligible. Then we also do the line integration over the RS portion. Here you can see that line integration line is directed along this direction, but electric field in region 2 E2T is directed along this direction. So we have a negative sign here. So line integration will give me contribution from RS as minus E2TL, and will not have any contribution from this portion SP because H is tending to 0. So finally, left hand side of the Faraday's law over the closed contour PQRSP will simply turn out to be, we have a contribution from PQ portion and RS portion, and it is E1TL minus E2TL. We also need to find out the right hand side of the Faraday's law. This is a surface integration. So here, if your time and space are independent, usually that's the case. In the next lecture, we'll discuss about time harmonic fields also, where you can completely separate out the time dependence of your fields. So space and time dependence of your fields are independent. So now what you are doing is you are doing space integration here. So ds is dependent on the space variable. Ds is the surface element. What we are doing is integration is over the surface S, so it's a space dependent term. Partial derivative is with respect to time, so it's a time dependent term. They are independent most of the case. In that case, you can take out the partial derivative with respect to time outside the integration. So you can write minus del by del T of integration of B dot ds over the surface S. So when you do integration of magnetic flux density over the surface, we get the magnetic flux. One more assumption here is that let's assume that this surface PQRS is very small enough that B is almost constant or not changing with respect to space variable inside this surface PQRS. In that case, I can take it out B outside the integration. So I can take out B outside the integration. We have minus del by del T of B dot integration ds over the surface S. When you do integration of ds over the surface S, you get surface S. So we can simply simplify the right hand side of the equation as minus del by del T of B dot S. B is the magnetic flux density, S is the surface you are considering. Let's assume that the area of PQRS is APQRS, and obviously the direction of the area would be normal to the surface. So now area is in the XY plane. So the normal to the surface in the XY plane would be along the Z axis. So right hand side of the Faraday's law will now become minus del by del T B dot. What is the area? Area is APQRS. That's the area of the PQRS surface, and direction is normal to the surface in the XY plane, so Z hat. And you can also look at the diagram. We have considered the length was L and height was H. So area of PQRS will become L into H. L is the length of the PQRS, H is the height of the PQRS. So in that case, I can replace A PQRS by L into H. So when I do dot product of magnetic flux density, which is in the three-dimensional, it's a three-dimensional variable, so it's changing with, let's say it's dependent on x, y, and z. In that case, B will have three components: bx, by, bz, along x-axis, y-axis, and z-axis. So when you do dot product of B with the unit vector z along the z direction, we will simply get bz. So finally, the right hand side of the Faraday's law will be minus del by del T of Bz into LH. But you know that H was tending to 0. If H was tending to 0, what is Bz L into H? Obviously it will be 0. This will be also tending to 0. So finally what you're getting is the right hand side of the Faraday's law is tending to 0. So you can write left hand side was E1 tangential L minus E2 tangential L, and right hand side now is equal to 0. So in that case, E1 tangential is equal to E2 tangential. So it means the tensile component of the electric field is continuous at the media interface. This is the first boundary condition for electric field. Let us consider a boundary condition for the electric flux density. So for the electric flux density, we'll use a Gauss law for electric field. What was that? D dot ds over a closed surface should be equal to rho b dv. Volume is the volume enclosed by this closed surface. So let us apply that. Here we'll make some assumptions. Like last time, we assume that the cylinder we're considering is small enough that D is not changing within the cylinder. This is one of the assumptions. Okay, let's go back to the diagram. What was the diagram? We are considering a Gaussian pillbox at the media interface. So this is the Gaussian pillbox. It's a small cylinder. We are considering height of the cylinder is h, and h is tending to 0. And top surface of the cylinder area will denote it by delta S, and bottom surface of the cylinder area also will denote by delta S. And the direction of, see, basically we are considering an interface in the rho phi plane. So whenever we consider cylinder, we should use the cylindrical coordinates. So the cylinder, this surface delta S is in the rho phi plane. This surface delta S is also rho phi plane. The interface is at z is equal to 0. So this is the z-axis. Interface is at z is equal to 0. When z is greater than 1, we are assuming that this is region 2. When z is less than 1, we are assuming it's region 1. So the coordinate system for this diagram and this diagram are different. So z greater than 0, we are having region 2. Z less than 0, we are having region 1. And this delta S is in the rho pi plane. And we are considering height of the cylinder is tending to 0. Here at this interface at z is equal to 0, we also assume that there is a surface current density of rho s. Is that okay? So now we want to find d dot ds over the closed surface, which is the cylinder here, Gaussian pit box. There will be contribution from this top surface, bottom surface, and from this curved surface of the cylinder. But the contribution from the curved surface of the cylinder will be tending to 0 as ice is tending to 0. So now we'll have only contribution from this portion, top surface and bottom surface. Look at the normal to this surface will be perpendicular to the surface that will be along the z-axis. Here, normal to this surface will be perpendicular to this surface that will be coming out from the surface, so that will be in the opposite direction. Normal will be in the opposite direction with respect to d1n, but d2n and normal are in the same direction. Normal should be coming out from the surface and it should be perpendicular to it. So when I do the integration, contribution will be from top surface will be d2n delta s, but contribution from the downward portion will be minus d1n delta s, and that should be equal to charge enclosed by the closed surface. The charge enclosed by the closed surface will be surface area into surface area is delta s and charge density is rho s. So finally we have the expression for the Maxwell equation, which is the Gauss law for electric flux density, electric field. So we can write d dot ds is contribution from the top surface and bottom surface equal to charge enclosed, which can be simplified as d2n delta s minus d1n delta s, and charge enclosed is rho s delta s. So now this delta s is common here, you can cancel it out. Finally what you're getting is d2n minus d1n is equal to rho s. The normal component of the electric flux density is discontinuous at the metal interface if there is a charge density present at the interface. And so d2n minus d1n is equal to rho s. This is the second boundary condition for electric field. Yeah, I have come across that many of the students are having many doubts in the derivation for magnetic boundary conditions, and it has been observed that in many of the texts and books it's not explained in a very detailed way. They assume that you already know the things, so I would try to explain it in a very proper way so that you clearly understand the derivation for magnetic boundary conditions. So let's look at this diagram. This diagram here is for finding the boundary condition for the magnetic fields. So what do I have? We have this coordinate system is similar to that of electric field boundary condition. You have x-axis, y-axis. Y-axis is along this direction. Z-axis is along this direction. So the interface is at z is equal to 0. The interface is at z is equal to 0 and it's in the xy plane. So now we are considering a closed contour in the xy plane. What closed contour is that? PQRSP. And also assume that there is some current density existing at the interface between the two regions. Interface is at z is equal to 0, we have region 1. When z is greater than 0, we have region 2, and z is less than 0. So now at z is equal to 0, at the interface, I assume that there is some current density. See, here dot means it's basically an arrow which is pointing out of your computer screen. So when arrow is pointing out and you look at it, it looks like a point. That's why we have a dot here. The direction of the current density is along the positive z-axis. Now it's coming out of the computer screen, so it's along the positive z-axis. So let's apply one of the Maxwell equations to find boundary condition for magnetic fields. So we'll apply modified Ampere's law or Maxwell's Ampere's law over the loop PQRSP. So this is the Maxwell Ampere's law. Closed contour integral of magnetic field intensity over a closed curve C should be equal to surface integration of your conduction current and displacement current, and this surface should be actually formed by this closed contour. So let's apply this modified Ampere's law over the closed contour PQRSP. Like last time, when I do H dot dl over this closed loop PQRSP, the contribution from here will be H1TL. Contribution from here will be negligible because delta H is tending to 0. Contribution from here will be, since the line element is directed along this direction, but H12 tangential is along this direction, we'll have minus H2TL. And we will not have any contribution from delta H SP portion because delta H is tending to 0. So the final equation for this left hand side would be contribution from PQ and RS, so it becomes H1TL minus H2TL. Let's look at the right hand side of the Maxwell Ampere's law. First thing is that, as I've already told you in the last class, in the previous discussion also, you have partial derivative with respect to time. You also have surface integration. One is time dependent, another is space dependent. But in EM theory, most of the time we consider time and space are independent. So in that case, I can take out this partial derivative with respect to time outside the integration and write del by del D of d dot ds. D is electric flux density, ds is the surface element. When you do integration of d dot ds over the surface, you get the flux, electric flux, which is coming out from that surface. So one more assumption here is that if I assume D is small, that PQRS area is small enough, very small, PQRS area is very small, then we can assume that the variation is negligible in that PQRS. In that case, D is almost like a constant vector. I can take it outside and do the integration over the surface area, S. So when I do surface area, surface integral over the surface is, I simply get the surface is. So this becomes del by del T of D dot S. And what was the area? We have length was L, height was delta H. So the area will be delta H into L. And this surface element is in the XY plane. So the normal to this XY plane would be along the Z axis. So the direction of surface element S vector will be along Z direction and its magnitude would be delta H into L. And when I do dot product of D dot Z, I get dz. So finally what I'm having is del by del T of dz delta H L. But delta H was tending to 0. Don't forget that. When delta H is tending to 0, this term will be negligible. So this term would be negligible. So what we have in the right hand side will be simply surface integration of J dot ds. What is J? J is the conduction current. So now there is one more confusion here about the J. So that's what I want to clarify in the next slide. J here is the volume current density due to free charge, and the Maxwell equation we have considered is for the free charge and current. And most of the time, volume current density is referred to as current density. So J is a volume current density. It's not surface current density. So now how do I define this volume current density? Volume current density is the amount of current passing through a unit area. Area should have a unit area. And one more point to be noted is that that area should be perpendicular to the direction of current flow. We are considering a unit area and that area is existing in perpendicular or normal to the direction of current flow. So now in that case, it's unit for volume current density is A is the amperes per meter square. Is that okay? So let us try to understand it from this diagram here. We are trying to define volume current density at a particular point. Let's say this is a conductor. So now some current is flowing in that conductor. Let's assume that the current flowing is delta I. Assume there is a surface element which is perpendicular to this direction of the current flow, and surface element is of area delta S, and length is delta L, and height is delta H. So this is a 3D structure, but we cannot draw it on the 2D plane. So this is the height of the surface element and this is length. So length is perpendicular to the direction of current flow. Delta H is also perpendicular because this is height. It should be actually coming out of this surface computer screen. So height should be coming out of that. So current is flowing now. And the area we are considering is perpendicular to the direction of current flow. And normal to this surface is also denoted by N, and current direction and normal to the surface should be in the same direction. In that case, only the surface element should be perpendicular to the direction of current flow. So for this case, I can define current density current density J, which is the volume current density at any specific point R, is defined as limit this delta S, which is perpendicular to the direction of current flow, is tending to 0, delta I by delta S. So we are actually multiplying current which is flowing divided by the surface element we have considered, which is perpendicular to the direction of current flow. That's why the unit of volume current density is ampere per meter square. Unit of current is A, unit of surface area is meter square, that's why ampere per meter square. So volume current density, but unit is ampere per meter square. Direction is along the normal to the surface. That was the direction of current flow. Is that okay? So now, how do we get surface current density from this volume current density? So by the way, what is the surface current density? We are going to use this surface current density, also volume current density, in the derivation for right hand side of the Maxwell equation we have considered. Ampere's Maxwell equation we have considered. That's why we have to clearly understand what is volume current density and surface current density. Okay, let us first define what is surface current density. Surface current density is the amount of current passing through a unit width. Consider this unit width perpendicular to the direction of current flow. It has to be perpendicular to the direction of current flow, and its unit is ampere per meter. So now let us try to understand it properly by using this diagram in the right hand side. So current flow for the surface current density should be in a thin layer. Its own current should be flowing in a surface. In the volume current density, current was flowing in a volume, but in the surface current density, current should be flowing in a surface. So current flow in a thin layer or surface. Imagine that you squeeze the height of the surface element we have considered, delta S. You squeeze the height to 0. What happens? You get a length, just one dimension, line of length. So when you squeeze, delta S tends to 0. Delta S in the previous diagram will simply become delta L. It will become a line now of length delta L. So in that case, the current which is flowing in the surface is delta I. Let's assume the line length is delta L. I'm showing a perpendicular sign. It's because I assume that current direction and this line, they are in the perpendicular direction. Don't forget that. So we can define surface current density now at a particular point R as, we'll denote surface current density by Js. S here means is surface. If I don't just put S here, it's a volume current density. When I put a S here, just to differentiate between the volume current density and surface current density notation, I put a S here. This is the surface current density. So now limit delta L tends to 0, delta I by delta N. So this is the ratio of delta I by delta L. So that's why unit is ampere per meter. Direction is along the perpendicular to the direction of the current flow. We can denote it by N. So I think you are ready to find out what is the right hand side of the Ampere's Maxwell law. So we have I store dl closed contour is equal to j dot ds. The contribution from the displacement current has been neglected because it was tending to 0. So now here also, if I assume J, the volume current density is almost same within the PQRS area, then I can take J outside the integration and just do this surface integration over the surface area S. So I get that is simply S vector. J dot S is what we are getting. What is the area of this PQRS was delta H into L, and this was existing in the XY plane. So the normal to the XY plane is along the Z axis. So we have J dot delta H L Z hat. I just want to consider this term here, delta H into J. What is delta H into J? When delta H is tending to 0. When I skews the surface to a, when I skew the surface delta H tending to 0, then I get a line. So in that case, I have to consider surface current density. So when delta S is tending 0, when I squeeze the surface delta S and tending the height is tending to 0, I get a line, so I have a surface current density. So when delta S is tending to 0, we define J delta S. When delta S is tending to 0, surface will no longer be a surface, it will become a line. In that case, current which should be flowing should be surface current. So that's why surface current density. Current density of the surface current is surface current density Js. So that's the definition of Js, surface current density. When delta S is tending to 0, volume current density will become surface current density. We call this Js as impressed surface electric current density at the interface, and obviously this will have a unit of ampere per meter. Anyway, this diagram in the right hand side will also illustrate the relation between the surface current density, volume current density, and current. So this is a bulk conductor we have here. What's the dimension? Height is delta S, width is delta W, length is delta L. It's a bulk conductor. So if I consider a current flowing in a bulk conductor, that will be volume current density. The current which is flowing in the bulk conductor is the volume current density denoted by G. But let's say if I consider a current which is flowing on the surface, then it will become surface current density. Current flowing in the volume is volume current, and density of that is volume current density. Current flowing in the surface and density of that is surface current density. So when I consider current flowing in a volume, I need to consider this area here. When I consider a which is normal to the direction of the current. When I consider the current density, I should consider this line which is perpendicular to the direction of current flow. When I consider volume current density, I consider this area which is perpendicular to the direction of current flow. When I consider surface current density, I consider this line which is normal to the direction of the current density. So now what's the relation between volume current density, surface current density, and current. No? So basically this right hand side is basically a current. No? H dot dl is equal to current enclosed by that closed loop. So we need to find the relation between volume current density, surface current density, and the current. So that's a relation. I will become simply area. What is this area? Delta H into delta L. This area is delta H into delta L. You multiply with the volume current density, you get the current. Or you can just combine these two terms, J delta H, it becomes Js. When you multiply Js with delta L, Js with the delta N, Js is the surface current density, multiply with delta L, you get current. Okay, so I think volume current density, surface current density, and the current flowing, the relation is very clear to you now. So now this right hand side, let's look at this right hand side. What was the direction for Js? So now this will become Js. Js dot Lz. Js was directed along the positive z axis. That's what I have shown in the diagram. We have a discussion on that. So now when I do dot product of Js and Js z hat, Js is the amplitude of the surface current density, z hat is the direction, dot product with Lz hat, I simply get JSL. So left hand side is H1TL minus H2TL, right hand side is JSL. So finally H1T minus H2T is equal to Js. So what does it say? It says that magnetic field intensity is discontinuous at the metal interface and the amount of discontinuous equal to the surface current if it was existing at the interface between the two media. Here's the first boundary condition for magnetic field. Let's discuss about the boundary condition for magnetic fields. Obviously, we'll use the Gauss law for magnetic field. B dot ds over closed surface is always equal to 0. There is no magnetic monopoles. This surface integration is over a closed surface. So we will use the same Gaussian field box we have used for the electric field also. So now, as you know that the contribution will be from the top surface and bottom surface. Curved surface contribution can be neglected because x is tending to 0. So in that case, B dot ds over the Gaussian field box will be contribution from top surface and bottom surface, and right hand side this is equal to 0 because we are doing closed surface integration for a closed surface of magnetic flux density and it's equal to 0. So we can write B2n delta S minus B1n delta S is equal to 0. In the top surface, the direction of the normal was in upward direction. In bottom surface, direction of the normal was in the negative z direction. Top surface it was in positive z direction, bottom surface it was in negative z direction. That's why we have a negative sign here. So finally what we are getting is B2n is equal to B1n. What it means is that normal component of the magnetic flux density is continuous at the metal interface. Okay, so we also have boundary conditions for current density. Look at this diagram, there's some slight changes here. The region 1 here is for z greater than 0, region 2 here is for z less than 0. The interface is at z is equal to 0. This is the pill box we are considering. Delta S is the surface area of this top surface and bottom surface, height of the pill box is h. We are considering a conductor in region 1 with conductivity sigma 1 and conductor with conductivity sigma 2 in region 2. Jn1 direction is along this direction, Jn2 direction is also along this direction. Normal to this surface should be outward from the surface, so it is along the same direction. Normal to this surface should be outward of this surface, it will be in the opposite direction. So now we can simply derive the boundary condition for current density. The boundary condition for current density is not derived from the Maxwell equations but from the equation of continuity, which is basically conservation of charge. What is conservation of charge? In the conservation of charge, whenever we have some time changing volume current density, we have the source for current density. Whenever there is a change in rho b volume current density, that is the source for current density. But let's say you consider steady state situation. In the steady state situation, there won't be any point where your volume charge density is changing. It has already attained a steady state. There won't be any change in the volume charge density at any point with respect to time. So that is what we're going to observe here. Let's say I consider a closed surface. I consider a closed surface. The current which is coming out from the closed surface should be equal to rate of decrease of the charge with respect to time of the volume enclosed by the closed surface. Obviously current is coming out from the closed surface, that is basically due to flow of charge, so minus dq by dt should be equal to I for a closed surface. Q can be also represented as rho b dv. B is the volume which is enclosed by this closed surface, and current I can also express as J dot ds over the closed surface. So as I have already told you, and the steady state, there is no point where there is change in the volume current, volume charge density. So this term del by del T of rho b is 0. So right hand side is 0. So now J dot ds over the closed surface, and we have considered Gaussian field box. Contribution will from top surface and bottom surface. There won't be any contribution from the curved surface. So finally what we have is Jn1 is equal to Jn2. So the electric current density normal component is continuous at the media interface. That's the first boundary condition for current density. We also have another boundary condition for current density, but this is actually implication of boundary condition of the electric current, electric field. We know that electric field was, tensile component of the electric field was continuous at the media interface. We know that, we have derived it. That was the first thing we have done in this class. E1 tangential equal to E2 tangential. You can express it in vectorial form also. N cross E1 minus E2. N is the normal to the interface. So now we also have a Ohm's law in point form. Ohm's law in the point form can be expressed as J is equal to sigma E. Ohm's law in the point form is expressed as J is equal to sigma E. So now I can replace E1 as J1 by sigma 1, E2 as J2 by sigma 2. In that case, I will get Zt1 by sigma 1 minus Zt2 by sigma 2 equal to 0. Simply, what I am getting is Zt1 by Zt2 is equal to sigma 1 by sigma 2. So it says that the ratio of the tensile component of the current density in region 1 and region 2 is equal to the conductivity of region 1 and region 2. Yeah, that is the derivation for boundary condition for electric field, magnetic field, and current density. Thanks for your attention. I hope to see you in the next